Welcome to the Explainer. Today, we're going to decode the secret language of industrial machinery. You know, every hum, every rattle, every single buzz, it tells a story. And if you know how to listen, you can figure out exactly what a machine needs long before it ever breaks down.
Just think about that for a second. What if, instead of scrambling to react to some catastrophic failure and all the unplanned downtime that comes with it, you could see it coming? That's really the whole promise of vibration analysis. It's a technique that turns all those rumbles and shakes into clear, actionable insights. Let's dig into how it all works.
So, here's what we're going to cover. First, we'll tackle the why this is so important. Then, we'll get into how we actually capture and decode a machine's signals. From there, we'll jump into the really cool stuff, how AI is changing the game. And finally, we'll look at what all this means for the future of maintenance.
Okay, let's dive right in. Why is listening to vibrations so incredibly critical? Well, it's really all about flipping the script, moving from a reactive, fix-it-when-it-breaks mindset to a truly predictive one.
At its heart, vibration analysis is all about predictive maintenance. It uses some pretty sophisticated algorithms to take a really complex vibration signal and break it down into its core parts. This makes it possible to spot the absolute earliest signs of trouble, way before they become big, expensive problems.
And what's amazing is just how much you can find. Look at this list. We're talking everything from a simple unbalanced shaft to the super subtle wear and tear on a single gear tooth. Analyzing vibrations gives us this incredibly detailed health check on the entire piece of equipment.
But of course, none of this incredible analysis can happen if you don't have good data to start with. And that all begins with one thing: capturing a clean, accurate signal right from the machine itself.
Before we even think about fancy algorithms, the single most important step is the physical connection of the sensor. Usually, that's an accelerometer. Because if you have a poor connection, you get a noisy signal. And as we all know, garbage data in, garbage diagnosis out. So there are basically three main ways to get these sensors on a machine. You've got stud mounting, which gives you the most rigid connection. That's best for getting really good high-frequency data. Then there are adhesives, which are perfect for when you just can't drill into the equipment. And finally, magnetic mounts are awesome for quick checks or temporary setups. The method you choose really depends on the job at hand. And just like mounting, it's absolutely crucial to pick the right tool for the job. You wouldn't use a sensor designed for low-frequency vibrations on a high-speed turbine, right? Different sensors are built for specific conditions, whether you're dealing with crazy high temperatures, big shocks, or just general day-to-day monitoring.
All right, so once we've got that clean data streaming in, this is where the real magic happens. The next challenge is to take this messy, complicated-looking waveform and turn it into something an engineer can actually look at and understand.
And here's what that looks like. On the left, you see the raw signal straight from the sensor. It's just a jumble of lines over time. Honestly, it's not very helpful. But then, on the right, you see that exact same signal transformed into a crystal clear frequency spectrum. Now we can see exactly which frequencies are there, and, just as important, how strong they are. So how do we get from that mess to that clean chart? We use an incredible piece of math called the fast Fourier transform, or FFT. The best way to think about it is like a prism for vibration data. It takes that one complex signal and splits it into all its individual frequencies, just like a prism takes white light and splits it into a beautiful rainbow.
And yeah, this quote pretty much sums it up. Without the FFT, all we'd have is that noisy, messy waveform. The FFT is the tool that turns that raw data into actual diagnostic information. It's what makes modern vibration analysis even possible.
Okay, so we've captured the signal and we've decoded it. Now, let's talk about how artificial intelligence is taking this whole process and launching it into the future. We're moving beyond simple diagnosis into true prediction.
A seasoned technician, someone with years of experience, can look at an FFT spectrum and spot the usual suspects. They know the telltale frequency spikes that scream bearing fault or misalignment. But here's the thing. AI can find patterns that no human ever could. For instance, a convolutional neural network, a CNN, can look at that frequency spectrum almost like a picture, identifying the unique visual fingerprint of a very specific fault. But then you have a different model, like an LSTM, which is brilliant at analyzing the sequence of data over time. It can connect a tiny vibration change today to a shift in plant temperature 6 months ago, a correlation that's just impossible to spot manually.
So let's break down how these models help you on the shop floor. First, anomaly detection. The AI learns the machine's normal heartbeat and just flags anything that's different. Then, classification. A CNN can be trained on past failures to say, hey, that's not just an anomaly. Its signature is a 98% match for a stage 2 bearing failure. And finally, prediction. An LSTM can track these trends over time to forecast, based on how this is progressing, that bearing has an 85% chance of failing in the next 700 operating hours. See the difference?
Okay, this brings up a huge question, one that every engineer and maintenance manager has to ask. If an AI tells you to shut down a multi-million-dollar production line, but you have no idea why it made that call, how can you possibly trust it? And that's where this really fascinating field of explainable AI, or XAI, comes into play. XAI is all about opening up that black box. It provides tools that show you exactly which data points or which features the model looked at to make its prediction. This is what builds the confidence and trust we need to really rely on these systems. So, you take these advanced sensors, you combine them with powerful analytics like the FFT, and then you layer on this explainable AI. What does all that mean for the future of keeping our most critical machines up and running?
Well, it means we're walking into a new era of what we can call proactive maintenance. The goal isn't just to predict that a machine is going to fail anymore. The goal now is to predict exactly why it will fail, and pinpointing the specific component, this bearing, that gear, this mounting bolt, that needs attention. And this is really the key takeaway here. This technology is moving at an incredible pace. Getting on board early isn't just about getting a leg up on the competition. It's about building the experience and the knowledge you need to really harness the full potential of these amazing new tools.
So let's just quickly recap the journey we took. We went from a physical sensor bolted onto a machine, to a raw signal, to a clean, decoded spectrum, and finally, all the way to an AI-powered insight that can stop a catastrophic failure before it starts. It's a pretty remarkable translation process when you think about it.
Look, the technology to understand the language of our machines is already here. It gives us this unbelievable window into their health and their performance. So the only question left is, are we ready to start listening? Thanks for joining this explainer.